Okay, so welcome to the second part of our tutorial. For this part, we're going to go through some like more recent results, and first I'm going to talk about some fine-grained analysis of buy many versus item pricing, and the generalization of buy many mechanisms for multiple buyers, and then Ariel is going to talk about buy K mechanisms, which is something in between buy many and buy one mechanisms. Okay, so to recap the first part of the tutorial, we saw that the main part of work in multi-item mechanism design is simple versus optimal, where we want to approximate the revenue of optimal mechanisms with simple mechanisms. We also saw that in order to get good approximations in this way, we need some assumptions on the valuation functions and on the, for example, assumption of independence over items, distribution of the items. And with no assumption, there is a unbounded gap between simple and optimal mechanisms. And our approach was to change the benchmark from optimal to buy many. Another line of work which we did not discuss much is the computational aspect of things, both about computing the optimal mechanism itself, or even simpler mechanisms like item pricing or bundle pricing. Now, note that in order to to formulate the optimal mechanism, we simply need to write down an LP, and that's easy to do. However, in order to be able to solve the LP, we need the support of the distributions to be small. And even then, the result of the LP is going to be complicated. There are ways, for example, duality-based mechanisms to deal with larger supports. But the main issue really is that the resulting mechanism that we'll get, the menu of options that we'll get, is going to be large and it's going to be impractical. Regarding simpler mechanisms such as item pricing, things are also not that good. In fact, approximating item pricing better than a factor of square root of n being the number of items, is MP hard to do, even for a restricted valuation function such as unit demand. So this points to a picture that we have two issues. It's both approximating the optimal revenue and being able to compute even simpler mechanisms such as item pricing. Now, here is an idea to deal with both of these issues. Now, what we're looking for is, what if we can impose some restrictions on the valuation function? So we are going to make some assumption on the structure of the valuation, but we would hope that in doing that, we would get both a better approximation and a better computational result. So this is the kind of structure that we're looking for. That's a result that we want. And in addition to that, we would like this structure to be sort of parameterized, so that we can imagine by changing this parameter in the structure, we can get, we can see the same parameter in the approximation results and in the computation. It will get a little more concrete in a bit, what I mean. The results that we're going to see now is due to work of Challa et al. Stock 22, so it's pretty recent. Okay, so the structure I was talking about, we started from here. First, let's consider this example. Let's say that I want to buy a chair, and there are different types of chairs that I can imagine: plastic, wooden, or I don't know, something more advanced. And let's say Ariel is also interested in a chair. We might have different values on these chairs, but what we do agree upon is that we both think that a plastic chair is the worst, and then a wooden chair, and then like a advanced chair. So we agree on the order by which we value these items, but we might have different values. So this describes a totally ordered setting where we have n different items, but all of the buyer types agree on the order of these items. And now getting more specific, we can imagine a special case of totally ordered setting, which is called FedEx and was first introduced by Fiat et al. In this setting, we can, this setting is really the totally ordered setting, but with only two values. And the way we can think about it is delivery times. Let's say I have a package that needs to be delivered by some deadline. If the package gets delivered before the deadline, I will get some value out of it. And it doesn't matter what day before the deadline gets delivered. Whenever, as long as it's before the deadline, I'm happy. But if it's after the deadline, then it has no value for me, so I'll gain value 0. This is a FedEx setting, and so basically in order to describe each buyer, you just need to tell me the value that they gain from the right time delivery and the deadline. So with these two numbers, we can define a buyer. And the important thing about FedEx setting is that it is sort of between single and multi-parameter setting. And that's why we're talking about it here. But really what it is that it's a special case of totally ordered setting. And actually about the question that was asked in the previous part, this FedEx setting is exactly where we see that the revenue of buy many and item pricing are going to be equal. So about totally ordered setting, the results that we know. So again, we would like to examine these structures in two settings. Approximation, the amount of revenue that item pricing gets with respect to optimal buy many revenue, and how easy it is to compute the optimal item pricing. So the approximation result that we get is that in the FedEx setting, we get the exact same revenue from item pricing that we get from buy many. And in the more general totally ordered setting, we can get a constant factor approximation to optimal buy many revenue via item pricing. So note that the result of that previous paper from the first part of the tutorial was that this constant really was a log n approximation. Now we'll make some assumption on the structure, we can get better approximation. Additionally, regarding computation of item pricing, they show that computing the item pricing in the FedEx setting can be done in polynomial time exactly. And they propose a p-task to find the optimal item pricing. So basically, they propose a polynomial time algorithm to find the item pricing that gets 1 plus epsilon approximation to optimal item pricing revenue. And they also show that finding item pricing is hard to do in the totally ordered setting. In fact, it is strongly NP hard to do so, even if we are assuming that each buyer has 3 distinct values. So even in a simpler setting of totally ordered, we see this hardness result. And just to note that the setting we considered in the totally ordered setting is unit demand. I'm just interested in one item, like which is a natural assumption in this setting, because if there's ordering over the items, then I'm just interested in the highest valued item in that set. So moving on from totally ordered and making things a little more generalized, we go to partially ordered setting, and we'll see here how we can parameterize the structure. Now let's say that instead of just buying a chair, I'm interested in assembling a whole home office, and so I need to buy a chair, a desk, and a monitor. Now I am again unit demand over each of these sets of items. I just want one chair and one desk and one monitor. But I might get any combination of these. So any combination of a chair, a desk, and a monitor. And again, we have some ordering over each of these groups. So again, all of the buyer types agree that the plastic chair is worse than a wooden chair than another chair, and so on. So a next step for this generalization would be to assume that rather than one group of items that are order, we have k groups of items that are each order. Again, generalizing this further, we can consider a general partial ordering, which can be described by a forest. So in this case, we have some items, some of them are comparable to the others, and some of them are not. So for example, in this example, 3 is comparable to 5. For example, value of 5 is more than value of 3, but 3 and 7 are not comparable, or 3 and 2 are not comparable to each other. And the valuation function that holds here is that if some item dominates the other one, for example, 4 here dominates 3, then we don't really need to have both of them in our set. If we remove the dominated item from our set, we are going to still have the same value. And this is how the value function is defined. And the parameter is defined as the width of this forest, which is going to be the size of the largest set where no two items in that can be compared. So for example, in this first example, I can't by default compare the value of a chair with a desk with a monitor. So here we'll have the width of 3. And in this example, again, well, the set that we're looking for is going to be 1, 3, and 7 because I can't directly compare their values. But I can compare the value of like 3 to 6, for example. So this is going to be the parameter that we define. Now, let's say that we have a partial ordering and the width of that partial ordering is k. Then they show that the optimal item pricing approximates optimal revenue, optimal by many revenue with a factor of log k. And regarding computation, well, they propose an algorithm that runs in polynomial time, but this polynomial now also depends on exponentially on k. So in order to get a polynomial time algorithm that computes a 1 plus epsilon approximation of item pricing, we need k to be a constant. But what I want to point out here is that this k really is changing from, in the general case, it's changing from 1 to n. And in the case that it's 1, it means that it's just a total ordering. And as k goes from 1 to n, there is less and less structure available in the valuation that we're imagining. And the approximation factor goes from constant to the log n that was proposed in the previous paper for the general case. So this k is really the parameter we're looking for, and it tells us exactly that what structure we need to have to get a better approximation and computation result. Okay, so and now we want to take a look at how the item pricing is computed. Well, as I said, and we're going to focus on the totally ordered setting. This can be generalized to the partially ordered, but we'll focus on totally ordered. So we are dealing with a unit demand buyer, and the valuations are totally ordered. And well, they propose a p-task, but here we are going to see a constant factor approximation because it's more representative of what happens. Okay, so our goal here is that we have this unit demand buyer and ordered values, and we want to find item pricing that is like optimal or near optimal. Now, the thing is that generally finding prices for a unit demand setting is more difficult than doing that for additive. And it's because in unit demand, if we change the price of one item, then it disturbs the price of others. But we are more able to separate things on different dimensions in the additive setting. So ideally, we would want to deal with the additive setting and not with the unit demand setting. Now, the question is, how can we convert this setting into an additive, and then maybe we can compute the prices there and then convert it back. Now, there is an easy way to do that because of the assumption that we've made on the valuations, and that's as follows. So basically, rather than looking at these items as ordered items, we can look at the first item as a base value and the other items as being upgrades on that. And these upgrade values are exactly equal to the differences of the value. So we can imagine our first item is the V1, the first upgrade is V2 minus V1, and so on. And in that sense, this additive buyer is going to be equivalent to unit demand. The only thing here is that for it to be really equivalent, I need to assume that in this additive setting with these new valuations, the buyer is only capable of buying prefixes of items. So like the buyer shouldn't be able to buy like this item 1 here and item n, because then we wouldn't have something equivalent in our unit demand setting. But if you're we are forcing the buyer to only buy prefixes of items, then if the buyer is interested in item I in this unit demand setting, that would be equivalent to buying items 1 to I in this additive setting. And the value and the payment that they would get is going to be exactly equal to unit demand. So far we made this reduction. We created this additive buyer, and if we force them to buy prefixes, then the revenue that they'll get is going to be exactly equal. But then the problem is that, okay, we're not really dealing with an additive buyer then, because we impose this restriction on the buyer. But the question is, what happens if we ignore this constraint? Like, is it possible? I know that if we have the constraint, the revenues are going to be exactly equal. But what if we ignore the constraint? Is the revenue that I'm going to get so far, is it going to be so far away from the unit demand one? And turns out that if we deal with it carefully, the answer is no, the revenues are not going to be that far away. And how's that? So in order to get this pricing, let's do the following. Let's start with the optimal unit demand item pricing, and let's call that pricing P1. Next step would be to round down the values to powers of 2, and by that we get the series of prices P2. And when we do this, well, we're going to lose a constant fraction of the revenue. And the other thing that might happen is that this rounding might create items with the same price for us. But because we are dealing with a unit demand buyer, when a unit demand buyer is given 2 items with the same price, well, they're always going to pick the item with the highest price. So if something like that happens here, we are going to just merge the 2 items and keep the higher value. The next step, as we saw, would be just to consider these differences to create a prefix buyer, create an additive buyer with the prefix buying constraint. And note that these 2 steps, like steps 2 and 3, generate the exact same revenue because we have the constraints still. And the last step, creating P4, would be just to consider the additive P4, but without the prefix buying constraint. So now we would like to show that this P4 gets a revenue close to P1. There are 2 observations we can make here. Let's say that, first of all, something to note is, okay, this is the P2, we made all the prices powers of 2, and in the third step, we made them differences of powers of 2. So P4 is the same as P3, so the P4 that we are dealing with is really differences of powers. Each price in that is going to be a difference of powers of 2. Now, what we claim is that, let's say that a buyer in P4, so an additive buyer with no constraint, is interested in some set T, which has items J1 to JB. Then we claim that if the buyer in P3, so an additive buyer with prefix constraint, wants to buy this set or a superset of this set, what they need to do is, well, they need to buy items from 1 to JB because they want a superset and they can't just buy prefixes. So they have to buy this T prime, which is 1 to JB. But more importantly is that doing so under P3 is not going to be that much more expensive than P4. In fact, it's just going to be twice that or some constant factor of that. And the reason this happens is precisely because we consider them to be powers of 2. We did the merging and they are now differences of powers of 2. Then the second argument is that if we consider now a scaling of P4, some appropriate scaling of P4, then we are going to get a constant factor approximation. The scaling factor argument here is something similar to what we saw in the previous part. But okay, so now that we know that the revenue of P4 is about the same as revenue of P1, it just suffices for us to compute P4, because what I said was that I assume that I know like the optimal unit demand pricing. I don't know that, so I need to somehow compute P4 and then using that figure out what P1 should be. And now the thing is, computing P4 is not hard. We can use a dynamic program and use this power of 2 prices. And then again, using the dynamic program, we'll also figure out where we merge the items. So this is the idea about how to compute a constant factor approximation item pricing. in the case of unit demand buyer with totally ordered values. Now, just a little bit about how we can generalize this to a p-task. First of all, rather than rounding down to powers of 2, we'll round down to powers of 1 plus epsilon squared, and this step costs us a factor of O epsilon in revenue. Now, the second step, which is a little different from the constant factor approximation, is that I said that when we rounded down to powers of 2, we merged the items which had the same price. We are not going to do that exactly, but in the case of p-task, but what we do is we are going to group the items in a way that items that are in the same group are going to be have close to each other prices. In fact, the prices are going to be multiplicatively close to each other, but the ones that are in different group are going to be multiplicatively far. And this is how we show that prefix buying is not going to be that much more expensive than buying just any subset of items. Okay, so to sum up the work of this paper, we saw that optimal mechanisms are complicated and impractical. For that, we decided to just focus our computing to simple mechanisms such as item pricing. We also saw that optimal is not good. It gives unbounded gap between that and simple prices, so we focused on buy many mechanisms. Previously, we knew that the gap between buy many optimal and item pricing is log n, but we were interested in finding out what structure we need to get something better than log n. So from basically constant factor approximation or exact value of revenue to log n. And in order to get that, we define this structure of order over items, where we start from FedEx, which was the case between single and multi-item. And we moved on to totally ordered and partially ordered. And as we made the structure more and more general, naturally our approximation and computation results got worse. But we saw how to increase and decrease the structure and get a better or worse approximation guarantee. And these results are tight. And the parameter K is really the parameter that was promised to govern and interpolate between FedEx and general setting and change the results for us. Okay, so another topic to consider is generalizing buy many for many buyers. So far, what we talked about the single buyer setting, where we take a sample from the distribution of the values that we have. But now we are considering many buyer setting, where we can imagine we have m items and n buyers. Now, well, a general natural idea is that, well, they need to be buy many, so we would want each buyer to face buy many mechanism. And there are different ways of this generalization that comes to mind. For example, we can imagine that the buyers arrive in sequence, in some predetermined sequence, and upon arrival, they see a buy many menu over the remaining items. Another way to generalize would be ex post buy many, where again, each buyer sees a buy many menu, but that depends on other buyers' bids. And a Bayesian model where it's the same, but then the menu that they see is going to depend on the allocation. The allocation and the prices that we see in the buy many menu is going to depend on the randomness and distribution of the other buyers. So these are all different ways that we can generalize. But one thing is common between them. There is a relaxation of buy many revenue that we can consider, which is the ex ante relaxation. And what we claim is that whatever model that we consider to generalize buy many, this ex ante is going to get an upper bound on the revenue of those. Now, in fact, it is going to be an upper bound on the models that I just introduced. The way we are going to define the ex ante revenue, buy many revenue is as follows. So, well, we can think about these M items that we have as like full allocations. And depending on how much of this allocation I decide to allocate to each buyer, well, I can get different buy many menus. So in order to define ex ante buy many revenue, we consider sum of buy many revenue when each buyer is given an allocation vector over the items. So instead of each buyer having the full allocation of the items, now we're saying that, okay, maybe they have it with probability half, or maybe they have half of it. We can imagine it that way. But we're going to consider these vectors in a way that this sum is maximized. And we ensure that each item is allocated at most one. So each xi here is itself a vector of length m, the number of items. Okay, so again, what happens is that this ex ante binary revenue is going to be an upper bound on the revenue of any generalization of by many to many buyers that we define. Now, well, the main result that we saw in the single buyer setting was that item pricing approximated a by many optimal with a factor of log n, log number of items. So any generalization we consider, well, we would like to see the similar result. So now let's see what item pricing will be when we have many buyers. Here we consider sequential item pricing. In this case, again, buyers appear in some order that we know. And when each buyer arrives, they see they're given basically an item pricing. This item pricing can be different from buyer to buyer. However, we want it to be predetermined, meaning that we don't want it to depend on the items that are remaining at that moment. Naturally, the buyer is only going to be capable of buying items that are available, but we just don't want it to be depending on what the buyers buy, the previous buyers have bought. So from the beginning, we know what the prices are going to be, and we assume that we know the order. Now imagine that, we define sequential item pricing in this way, and imagine SREF to be the optimal item pricing, the sequential item pricing that achieves the maximum revenue. So what we can prove here, again, due to a result of Challa et al., is that if we have n independent buyers, and again, that are unit demand and m items, and we know the order of their arrival, then ex ante by many revenue is going to be at most log m times the optimal sequential item pricing revenue. So we see a similar result here if we consider this kind of item pricing, sequential item pricing. Okay, so we are done here. If there are any questions, but then we are going to move on to Ariel to talk about by-K mechanisms.
Great, thank you. So hopefully everyone can see my slides. So as Rojin was mentioning, here's a nice way to think about by one and by many mechanisms. So we can think of like the restriction to be kind of like a dial where the by one setting has a seller that is unrestricted. The by many setting has a seller that is very restricted. But what do we get when we turn that dial is, we get an improved worst case approximation for opt and simple mechanisms, right? So, we go from being unbounded to being logarithmic in the number of items. And so a natural question, this revenue gap, this from infinite to log n, it must drop off somewhere, right? It's kind of like a continuity argument. Like somewhere when I'm turning this dial, hopefully we go from infinite to finite, right? And this is kind of a question that we set out to explore and what motivates this definition of a by-K mechanism. So a mechanism is by-K incentive compatible if the buyer would prefer to buy a single bundle over any multiset of at most K bundles. So here we're being explicit about the number of interactions the buyer can have with the mechanism, right? We're trying to set like a cap on it and see what role this plays on revenue approximation. So more specifically, if you give me a mechanism, we'll say that it is by-K incentive compatible if, your favorite allocation, AI, for a price PI, you prefer that to buying any multiset of size K and paying the sum of their prices, right? So the challenge here is that this A of S function is actually highly nonlinear. So if I have a set of allocations A1 through AK, what is the probability that I get item I? It's 1/n probably than all of these allocations, right? And because we have this like product of allocation vectors, this problem becomes very nonlinear very quickly, right? You can see how as k increases, as I'm allowing the buyer to, mix more and more bundles, the degree of, these constraints and the number of these constraints would grow very, very quickly, right? So they're not easy to deal with. So let me give you an example just to try to formalize notions or settle notions a little bit more. So suppose that I have some mechanism M that allocates a quarter and charges 1.5 for one allocation, and then for some other allocation gets you a half for 4.5. And let's say this is the optimal by one mechanism for some distribution, right? So a buyer with type 2-4 walks into the store. What utility does this buyer get for the first allocation? They get utility 0, right? So I designed it so that their utility was 0. Their utility for the second allocation is below 0. So they would prefer buying A1 over A2. Great. But what if they could buy A1 twice, right? So what would buying A1 twice look like? So if you flip a coin with probability a quarter of being heads twice, the probability that you hit at least one head should be this 7 over 16, right? You notice here that this quantity is slightly sublinear, right? In the allocation probability, intuitively or maybe ideally it should be like a half, right? If you get a quarter, you should expect to get it half of the time. But because if you flip head twice, then you only get the item once, right? You cannot win the item twice. So that's why we get the 7 over 16 number. So it's a little lower. It's a little below this linear growth that you would expect. And so now buying this allocation twice, it does net the buyer more allocation, but because the price increases linearly and the allocation does not increase, it increases sublinearly. Their utility was 0 before, now it's going to be below 0. So even if they could buy A1 twice, they would still prefer not to. They would rather buy A1 just the one time. And even adding it more times is not going to help, and combining it with A2 is also not going to help because A2 is already giving you negative utility. So even if the buyer could buy anything twice or more than twice, they would still prefer to buy it just once, right? So now here's another buyer who's going to walk into our store with types 3 and 9. They would get utility 1.5 for either A1 or A2. I designed the valuation so that was the case. Let's say that they buy allocation A2, just, they break ties in our favor. What would happen if they were to get A1 twice now, right? So it's still the same expected allocation as before, the 7 over 16, 7 over 16. But now, because of the numbers themselves, it turns out that their expected utility for this allocation is better than their expected utility for buying A1 or A2, right? So if you do this little math here, you get, 7 times 3/4, it seems, which is, 2 and a quarter, which is a little bit more than, so the utility is at 2 1/4, which is more than 1.5, which is more than 1.5, which is the utility before. So they would rather buying A1 twice than A1 or A2. And this is a problem from our perspective, right? So this mechanism would not be by 2 incentive compatible. All right, so this is just a reminder of our definition. So let me tell you what the main results of our work were. Actually, first, let me introduce a claim. So, I'll say for any distribution D, the by 1 revenue is, weekly better than the by 2 revenue, weekly better than the by 3 revenue, and so on until you hit the by many revenue. And then, this is obviously better than bundling or selling separately because bundling and selling separately are instances of by many mechanisms, right? So here's an interesting observation and something that we conjecture on our paper. So, we conjecture that there exists a simple distribution such that for any k, the by k revenue is strictly better than the by k plus 1 revenue. And we prove this computationally for k equals 4. The instance that we have is actually very, very simple. It has 2 items and it has support size 3. And even just for the small k that we show, it already proves that, these restrictions are not empty, right? That there is loss in revenue as you further restrict the seller's choice of mechanisms, right? So now let me tell you about our main results. So the main result is that for any correlated distribution, for an additive buyer, the optimal by n mechanism is no better than BREV times a factor of O of n squared. In other words, bundling recovers a fraction of 1 over n squared over the optimal by n mechanism. And so, you might think back to like the CTT results that Rojin was talking about and say, well, they were getting a log n approximation for additive buyers. What's going on here? Why are you getting n squared, right? So I'm just going to argue quickly that because, we use bundling rather than item pricing, we are doomed to get no better than a factor of n, right? That's a problem of the benchmark that we choose. And this is just from the fact that we know that there is already a gap of n between bundling and selling separately for some distributions. And because they're both by many mechanisms, no by k mechanism could be at most n times bundling, or there exist instances, there exist distributions for which the optimal by n mechanism is better than n times bundling, right? So, this is the right order of magnitude for our result. Maybe there's some improvement that can be done, but you cannot go below order of n here. And in particular, this result, if you just instantiate it for n equals 2, already shows that, the Hard-Nissan counterexample falls apart, right? It shows that bundling recovers a 1 over 8 fraction of the optimal by 2 mechanism. So it turns out that, this weird distribution, if you restrict the seller to be, let's say, a little more reasonable, then, bundling actually gets a reasonable fraction of the optimal revenue, right? It no longer has this property where, opt was unbounded and bundling only got a, finite amount. So the proof techniques derive from a recent paper with Thomas and Weinberg and myself for actually proving lower bounds, so for proving inapproximable distributions. So the first step, and this is a very, very, very rough sketch of this proof. The first step is we define a measure for a distribution, takes a distribution and it takes a by k incentive compatible mechanism. And the property is that this measure upper bounds the ratio between the by k revenue and bundling up to a factor of k. And this measure is kind of like a generalization of this gap notion I was talking about in the first half of the talk. And then the second step is actually just showing that for the specialized case when k equals n, this measure is at most n, right? So if you combine steps 1 and 2, then you get the result that I claimed, right? You get that bundling recovers a 1 over n squared fraction of the optimal by n revenue. And for more details, you can see my co-author George's talk at EC. It's on the calendar. You can find the talk if you're interested. We have some additional results. So we also show that for a monotone buyer, you get something similar, except that there's now an exponential factor in the approximation. This should not come as a shock. Monotone valuations are, we know positive results for them are more rare than for nice classes of valuations like additive or unit demand. But we use this result as kind of like a proof of concept for our proof approach and our proof techniques, right? And to prove the power of this new framework. And due to the observation that Rojin mentioned from the CTT paper, our upper bounds also hold against adaptive buyers, right? So we get that for free from their paper. We have some lower bounds as well. So it turns out that if k is a little below root n, there exist distributions for additive buyers for which the by k revenue is exponentially better than the revenue of bundling, right? So again, here we don't quite get like the huge hard-Nisan in approximability gap. It's not unbounded, but we know that it's at least exponential, meaning that no simple mechanism can get like a good approximation anyways, right? And in fact, our instance is deterministic. The mechanism that we use is deterministic, I should say, not the distribution, of course. The mechanism we use is deterministic, so it also holds against adaptive Bayers. So it's a very strong lower bound. And we prove a nice result that is it's kind of like dual to this, or kind of like the flip side of this is that if k is over this threshold of root n, then actually bundling gets a Pauli factor from the optimal deterministic by k revenue, right? So, it seems that there's a strange threshold here around root k, like some weird behavior happens around root k where, above root k, maybe there is hope for good results, and below root k, we know that, approximations are going to be not nice, right? Great. So to summarize what we've talked about during this tutorial, we introduced this concept of by many and by k mechanisms, and we said that they have some nice properties. In particular, they have a finite worst case gap approximation for all valuation classes and for arbitrary correlation. This was not the case for by one mechanisms due to this hard-Nisan construction. Rojin mentioned that by many mechanisms have this revenue continuity property, which is very natural. It was just saying that if you have two distributions that are close, then the revenues should also be kind of close. And by many mechanisms also preclude super additive mechanisms or prevent the seller from exploiting the buyer. This came across the multiple examples that we gave during the talk. And these are natural properties. We would like mechanisms that have these properties, obviously, because we interact with them in real life. Like I don't know of a setting where you go somewhere and the pricing is super additive on individual prices. There are a lot of problems still with by k and by many mechanisms. We don't know how to compute opt like in general. It's not like the by one case where you can just write an LP and that's that. Here the problem is very nonlinear. And so it's unclear what the computational complexity of designing or computing a opt by k or opt by many mechanism would be. And it's also even hard to test if a mechanism is by many or by k. I'm not sure exactly the computational complexity of this, of deciding if a mechanism is by many or by k. And it's unclear if opt is structured in a nice way. So Rojin, I guess, mentioned that we do know of like some settings under which the opt actually matches the by many opt, and that's nice. We would like to explore more structured settings and find more of these nice results. And so here's some future directions that are interesting to think about. So extending by many or by k mechanisms to multiple buyers, this is very natural, and Rojin talked a little bit about this. Initiating a study of by many or by k mechanisms for independent distribution. So we introduced them as a way to get around these hard-Nisan weird correlated distributions, but they could also be very useful in improving approximation factors for independent distributions, right? In particular, maybe the benchmark is also just too high in the independent case, which is why we cannot get a better than a 6 approximation for independent items, right? Then maybe actually formalizing these computational issues that I talked about, it would be nice to know how hard it is to compute opt by many or opt by k mechanisms. And then this is something extra that I think is interesting. It's an open question from a paper by Babayev, Nisan, and Rubinstein from EC a couple of years ago, which is just studying the gap between the deterministic and subadditive deterministic mechanisms for independent items, right? So we saw that for correlated items, there's definitely a gap, right? We gave examples of deterministic and subadditive deterministic mechanisms where there was a revenue gap. We don't know if such a gap exists for independent items, And in particular, it would be nice because it would also like prove a small separation between deterministic and by many mechanisms for independent items, right? Remember that Rojin talked about how, if you're subadditive and deterministic, then you have the by many property. And other directions here. I mean, we introduced these mechanisms as a way to get around the hard Nisan constructions. So any other ways to attack this result are also valid, right? Like like I said, you can either make assumptions on the distributions or argue that the benchmark is too strong. So if you have other ideas of like what are other reasonable benchmarks to study, then I'm sure those would make interesting results as well. And with that, we'll thank you all for attending. We'll thank again the organizers for putting this together, and we'll open the floor for questions. So please, thank you all.